Okay, I'd like to thank the organisers for putting together this diverse and interesting programme, and thank you very much for the invitation. It's great to be here. I was in Cambridge for 14 years, and I never managed to stand on this stage before, so I feel like I'm making progress in my academic career now. So I guess this title is somewhat vague. I suspect that probably 80+% of the talks in this entire conference you could probably use the same title for, which is deliberately somewhat vague. I mean, it's a bit of a sort of grab bag of things out of various papers I've written at various times, but hopefully there is a bit of a unifying theme. And if anything, the unifying theme is me trying to think about simple problems. This is my style. I don't like to think about hard problems until I can understand the simple problems first. So when I talk about discrete random variables, what I'm going to be talking about is random variables on the integers. This is nearly always the setting. So just random variables that give us, and in fact, positive integer values. I'm not going to be doing things on Riemannian manifolds or anything like that. It's all going to be very, very concrete. So the manifesto is really this, and the kind of starting point is this observation. Gaussian random variables are lovely. Normal distribution is everybody's favorite random variable. And when you start thinking about it, there are various senses in which this is true, right? I mean, you've probably got your favorite sense yourself, but here are at least 4. Gaussian random variables are maximum entropy. You fix the variance, the normal maximizes the entropy. People know that. They're stable. You take 2 random variables, you scale them, you add them together, you do linear transformations of Gaussians, you get more Gaussians. More in the theme of this meeting, they're the case of equality and the entropy power inequality. I mean, Shannon knew that they were the case of equality. I'm not completely convinced he knew that nothing else was, but he certainly stated this, and that if you take entropy powers and you get equality, then it must be that the Gaussian is the thing that's giving you equality. And more than that, because of that, it turns out that the EPI actually implies Gross's log Sobolev inequality, that the EPI came before, but actually gives this log Sob inequality. And then there's this whole world of information geometry that, in general, there are nice, depending which way you look, convexity or concavity properties of things to do with Gaussian random variables. So, for example, the entropy of Gaussian random variables is a nice function that we can understand the concavity of. So this talk is really my attempt to kind of do a grab bag of things that maybe addresses some of these issues, and to try and see what place is played by particular discrete random variables. So I'm talking about random variables that you learn when you first start learning probability: Poisson, geometric, binomial, things like that. So my starting point with all of this is really the stability. We know that if we take 2 Poissons and we convolve them together, we add 2 independent Poisson random variables, we get another Poisson. So really I want the Poisson to be at the heart of what I want to do a lot of the time. The Poisson feels very fundamental in all of this. And the other kind of thing I'm looking for is some kind of idea of log concavity plus. So in other words, Gaussian random variables have a lot of nice properties, one of which is if you take the log of the density, you take a second derivative, you get a constant. And that, in terms of this Bakry-Emery theory, is actually really, really fundamental. So I'd like to understand what the kind of corresponding property is of discrete random variables. So if you want a reference on all of this, a lot of this is written up in this proceedings of this IMA workshop that came out just over a year ago. So a lot of what I'm going to talk about is there if you want to follow this up. So there's an outline of the talk. I'm not sure I'm going to get through all of that, but I'll see how I get on. So as I say, I want some sort of idea of log concavity plus, and it turns out there is something in the literature that exists and that does a lot of this work for me. So if I write pi lambda for the Poisson lambda mass function, there is something called ultra log concavity, which is probably about 20 years old now. It goes back to Pimentel and Liggett in the late 90s. And what they said is they defined a class of random variables that, well, essentially this is the key property, the property that the ratio of the mass function of our random variable v to the kind of reference Poisson mass function wants to be log concave. So if you think about that and you kind of write it out another way of writing it is, you know, you do this, you do some cancellation. What you find is that PV squared is bigger than PV plus 1, PV minus 1. That's sort of standard log concavity. But actually, ultra log concavity, as the name suggests, is just a little bit more, that you want V times this to be bigger than V plus 1 times that. If you think about it, then that holds with equality for the Poisson. I mean, this is where this has come from. It's designed to hold with equality for the Poisson. But this turns out to be a very useful property. So it's a decent sized class. I mean, it's a class that includes Bernoulli sums. I mean, I guess I should say this, that we're in the Isaac Newton Institute, and people call this Newton's inequalities. The fact that the sums of independent Bernoulli random variables are ultra low concave actually probably goes back to Newton. But it's, you know, it's a big class. It includes Bernoulli sums, it includes Poisson, it's preserved on summation. It's a nice class. It's a class that we're happy to deal with. And so I really got into this sort of right at the end of the time when I was in Cambridge. I think this was almost the last paper I wrote when I was in Cambridge, that you're able to prove a maximum entropy property for the Poisson under this condition, that if you start trying to do sort of standard, you know, Gibbs variational arguments, the Poisson isn't very nice. I mean, you can write down a condition under which the Poisson is maximum entropy, but it involves something like the expectation of the log of x factorial. And I kind of feel like nobody's ever actually calculated the expectation of the log of x factorial, other than because they wanted to do a maximum entropy argument. It's not something that crops up all the time. It's not a natural condition. Whereas if you think about it in terms of ULC, actually you do end up with a more natural condition, I think. So what you end up with is the following theorem. So if you have x, which is, it's ULC and it's got mean lambda, and you compare it with y, which is Poisson with mean lambda, then the entropy of x is less than or equal to the entropy of y. So in other words, within this class, within this ULC class, the most random, the maximum entropy random variable is the Poisson. And equality characterizes the Poisson. So it's a nice sort of clean statement. And you know, it's kind of independent to the way that people, you know, often deal with these things. So Peter Harmos had looked at this before and had an expression to do with binomial sums. He had a kind of corresponding argument that said that the sum of the sum of independent Bernoulli random variables also has the same properties. So this is just sort of widening out the class ever so slightly. So this was the sort of first piece of evidence that I felt that ULC was a useful property. Another property requires slightly more explanation. So there is a construction to do with discrete random variables which is called thinning. So thinning actually goes back to Rennie in the 50s, and I think it's sort of slightly strange that Rennie thought of thinning and Rennie thought of Rennie entropy, but I don't, as far as I'm aware, I don't think he ever put them together. I can't find a paper where these two ideas are combined. It's sort of slightly odd. So the construction is this, that what you do is, given a random variable y, you define what's called the alpha thinned version of y. So I'm going to write T alpha of y is the alpha thinned version. So the way it was defined originally was it was defined with point processes. So if you have a point process, you have some collection of points. You go through and you independently knock them out. But what you do is you have some parameter alpha, and that's your kind of killing parameter. And so what you do is you go through and independently at random, you just look at each of these points and say, are they going to survive or not? And so you have a count distribution before you thin, you have a count distribution after you thin. So you thin according to this parameter alpha. So again, this is a kind of nice thing because thinning turns out to preserve various parametric families. So for example, if y is Poisson, T alpha of y is also Poisson. I think I remember having that on an example sheet sometime in, it may have even been first year probability here, which horrifies me to think about now, but you know, it's a sort of wellish known operation that sort of keeps things honest. And the reason it's useful in this context is there is evidence to believe, and some of this is on the next slide, there is evidence to believe that thinning by alpha is the discrete equivalent of scaling a continuous random variable by root alpha. And if you go into a lot of proofs of the entropy power inequality, it's not sort of directly there, but you start looking a bit under the hood. then you actually start to see that very often somewhere in there is a scaling step. There's a step at which you scale by root alpha, and you know exactly what happens to the entropy when you do. Now, that makes everything nice in the continuous case. There isn't a corresponding result in the discrete case, which is somehow why the discrete case is messier. But on a kind of high level, thinning by alpha is the same as scaling by root alpha. And in particular, it plays nicely with the maximum entropy condition in terms of the Gaussian having a variance condition and the Poisson having a mean condition. So here is the kind of thing that you can prove. I mean, I don't really want to say a lot about this. This is a result about the entropy of linear combinations under thinning. So probably the best thing I can do is if I put this up and then I'll put below the famous Artstein, Bull, Bart, Knorr result, then I want you to look at these two and say, oh yes, these look quite similar. This is the kind of take home here. So if you remember the setting of this was a statement to do with, so here little h is now a differential entropy. We're talking about continuous random variables. They proved this result. This is what settled this kind of 50-year open question about whether entropy was monotone in the CLT regime. They proved this result that actually gives us a very strong form of the entropy power inequality, that this turns out to give us strengthened EPI from this kind of linear relation. So what have we got? What we've got on the left-hand side is we've got the entropy of a linear combination of the x's. So the x's are weighted by the root alpha i's, and it's a sum from I equals 1 up to n plus 1. It's a n plus 1 term sum. And we're comparing that on the right-hand side with the entropy of a sum that has one fewer term in. So this term doesn't have the jth random variable in. So what we're saying is that the entropy of the linear combination of the x's, of the n plus 1 x's, is bigger than the average of the entropy of the n term sum. So that was their result. And so what we were able to do was to show that essentially the same result holds for discrete random variables under the ULC condition. So under the ULC condition, if our x's, our xi's are all ULC, then formally you get exactly the same expression. The only difference is that, as I say, we've changed a scaling by root alpha to a thinning by alpha, and we've changed the little h to a capital H, but that's the only difference. So formally this looks absolutely the same. So this is again maybe some evidence that this ULC condition is nice. It turns out that you can actually do even better than that. If you want the same result for relative entropy, you can prove it without any restriction on x, that it's true for relative entropy even without the x's being ULC. So if you prefer relative entropy to entropy, and maybe you should, then actually this result is absolutely the same. It's the completely corresponding result. The only difference is the scaling by root alpha and the thinning by alpha. Okay, so at this stage I got excited, and this is sort of 2010. I thought, well, this is obviously the natural property. ULC is really important. I just need to figure out everything else based on this now. And then I got stuck for about 5 years on this. Things didn't seem to work out as nicely as they should do. And then I went to Dominique Bacry's birthday conference in Toulouse in 2014. And I actually started thinking about this sort of French Bacry-Emery way of thinking about random variables. And actually it turned out that maybe I had the wrong definition of log concavity plus. Or at least there is a different definition of log concavity plus that I should have been aware of, and that maybe under this other definition of log concavity plus, things work out better. So this is what I want to tell you about next. So this is another definition of log concavity plus. So if you remember what we did with the previous definition, we had this idea that we would look at the p of x squared and compare it with x minus 1 and x plus 1. And there we were kind of tweaking it by a sort of multiplicative factor. We were weighting one term bigger than the other term. But what it turns out is that there is this definition called C-log concavity in this work of Caputo et al. That they look at the sort of standard log concavity thing, and then they divide it by a slightly odd-looking factor. They divide it by pvx plus 1. Now this isn't at all obvious why you do this. So to unpack it slightly, if you look at it, what you've got is you could rewrite this as a difference. You could write this as a difference of the x over x plus 1 term and the x minus 1 over x term. And if you think about it, in the Poisson case, if v is Poisson, then each of these terms, this first term, for example, is you get an x plus 1 factorial on the top, you get an x factorial on the bottom, and then there's a factor of lambda. So essentially you've got x plus 1 over lambda minus x over lambda. So what you get is that in the Poisson case, this quantity that I'm calling EV of x turns out to be identically equal to 1 over lambda. So this is sort of designed again around the Poisson case, but maybe not in quite such an obvious fashion. So so in the Poisson case, this turns out to give us a nice answer. This EV of x doesn't depend on x at all. So what we'll do is we'll say, okay, we'll say that's giving us motivation. In general, we'll say that a random variable is C log concave if this quantity, if this difference of ratios is greater than or equal to C. So if for some constant C, this difference of ratios always beats C, we say that the random variable C is, the random variable V is what we call C log concave. So this is a slightly different take on log concavity plus. I mean, again, it's designed around the Poisson. We know that this is going to hold with the Poisson. We know that we can just say that the Poisson is 1 over lambda log concave. But it turns out to actually fit quite nicely with this other definition. It turns out that if a random variable V is ULC, then it is also C log concave. It's a kind of exercise in sort of playing around with ratios and things like that. But if a random variable is ULC, then it's also C log concave, and the sort of C log concavity factor is PV1 over PV0. So in other words, essentially you have to fix the degree of log concavity at the bottom. This sequence of differences gets bigger and bigger, and so the worst case is the case right at the bottom of the hill. So essentially this is kind of broadening out the class a bit. We're no longer restricting ourselves to ULC. We can look more generally, we can look at C log concave. And the nice thing about this as well is also, you know, ULC, either you're ULC or you're not. Whereas here there is this sort of parameter to play with. There's this C here, which is nice for various reasons. It gives us a little bit of flexibility in defining the class. And so what I was able to prove using this kind of machinery and using the sort of the discrete version of the Bakary-Emery theory is to prove a log sub inequality that looks something like this. Now, again, this probably needs a little bit of unpacking. I mean, this is the statement as it appears in the paper. The paper was in the annals of IHP, so I was writing for a French audience. And so there's an important thing here, which is that when you write an entropy in French, you don't put a minus sign in front of it. You know, it's one of these sort of slightly odd things here, and you know, as long as we're still in the EU, I think I should probably stick to this convention. So when I say ent VF, probably for most of the people in this room, what you're thinking is that this is really a relative entropy. You know, so if you think about this as a relative entropy, what this quantity is it's a sort of, it's the sum of Vx log f. So if you're thinking about this f as being a ratio of probability distributions, you know, this is what you might expect. And then here there is a factor that's the sum of Vf log the sum of Vf. So obviously if f is a ratio, you know, it's one probability distribution over V, the sum of this Vf will just give us 1, and so the log will kill it, and so what you'll end up with is just a sort of straight relative entropy. But this is, you know, for whatever reason, this is how these things are stated in the literature. So it's an upper bound on relative entropy, if you want to think about it like that. And so what you get is you get that there's an upper bound on the relative entropy, and you see the sort of standard Bakary-Emery sort of factors coming out here. There's a 1 over C factor here. So within the C log concave class, if you're C log concave, that tells you what the factor is outside this. And then the right-hand side is a slightly odd-looking thing, but it's Vx times this, again, it's sort of slightly relative entropy-looking thing. It's fx plus 1 log fx plus 1 over fx minus fx plus 1 plus fx. So it's not an obvious thing to end up with on the right-hand side. But, I mean, a few things to say in the defense is this is a sharp result. So in particular, if V is Poisson and fx is exponential, so it's e to the ax plus b, which again, if you want to think about this in the relative entropy world, this is saying if V is Poisson with one parameter, and then you're comparing this with a Poisson with another parameter, in that case, you get equality, that both sides of this are exactly equal. So there isn't any room to kind of tighten it.
Can I ask you, is this right-hand side somehow related to Fisher information?
Yes. Yes, it is. Yeah, right. So this is a way to think about it, that it is a kind of discretized form of Fisher information. I mean, somehow Fisher information, you have again, it's to do with this difference between left and right derivatives that I think we talked about the other day, that this is what you come out with. So there is a standard form of log Sobolev for discrete random variables, and actually it has more terms than this. So what you usually have is you have fx plus 1 minus fx log of the ratio, and that's more standard, but this is better. This is strictly smaller. So yes, it's proved using this discrete Bakry-Emery theory. And so yes, that there are various versions of log sob in the literature before. I mean, maybe I just put them all up together. So if you think about this in terms of relative entropies, you can write this as saying that the relative entropy from P to Poisson is less than or equal to the relative entropy from what's called the size bias version of P to P itself. So the size bias version is you scale the random variable by x and you divide it by its mean. So that was a known result of Wu. That was in the literature, proved I think using stochastic calculus by Wu and proved more directly by you. So this result follows from my result. You can also think about linearizing the log here. If you linearize the log on the right-hand side, what you get is you get here, on the right-hand side, you get Vx, and then this delta fx squared over fx. This delta fx is a finite difference. So you get the squared finite difference over fx. That was a log sob inequality that was due to Bobkov and Ledoux, I think, in '98. So this kind of tidies various things up like that. So it's, again, some evidence that if you have the right form of log concavity, then you can prove some useful things and you can sort of tie together some things that were in the literature already. Okay, so I want to kind of talk about something else that I've already alluded to at this meeting, which is this Shep-Olkin conjecture. So I kind of talked about this already in the problem session. So that just to remind you what the setting is, that the setting is this: you have n independent Bernoulli random variables, and you have a vector of parameters. So you have parameters p1 up to pn, and so what you can do is you can write, say, fp of k to be the mass function of the sum of these Bernoulli random variables, and then you can consider the entropy of that sum. So what we can do is we can say, I mean, we can just, if we like, index it by the parameter. We can say h of p is the sum of, f log f, where the f is defined in terms of these symmetric functions of these p's, however you want to think about it. So there's the machinery. You have the p's, you spooge them together in a particular way to get the f's, and then from the f's we look at the entropy of the f's. What I'm emphasizing is this isn't just the entropy of the p's as a vector. That's a somewhat easier question, right? So it's the entropy of the sum of these Bernoulli random variables with these parameters. And so, as I say, dating back to 81, Shep and Olkin conjectured that this was a concave function. So if you act on this vector p as a function of this vector p, then h of p is a concave function. So probably the first thing that you can do to simplify this is to think, well, if we're talking about this being concave, you can think about this as being concave in a particular direction. So in other words, although this feels like it's a problem to do with n parameters, actually what you can think is, if you're saying, well, we're concave at a point, you can just think about a line going through a point in that particular direction. It's enough to say that, going along that line in that particular direction, the entropy is concave. So we can kind of reduce to that case. We can just write it as a sort of affine form. We can say pi of t, it's a linear combination of pi of 0 and pi of 1, but we just smoothly interpolate the parameters in between. So what was known about this? Well, not a terrific amount. This is my evidence that not many people worked on this. So n equals 1 is pretty obvious, right? N equals 1 is just the entropy of the standard Shannon entropy of a single random variable. We know that. Shep and Olkin claimed, and they didn't even write down a proof, and it's not obvious if you even try and write down a proof of this. They claimed it for n equals 2 and 3. I mean, I have no reason to doubt it, but I'm interested to know how they did it. I mean, I suspect it wasn't pretty. They also proved the binomial case. They proved that if pi of t was equal to t, so in other words, all of these random variables are going binomial in the same direction at the same speed, then this is true. And that's not obvious. Mateev proved it about the same time, but you need a bit of work to do that. And then there were a couple of kind of little breakthroughs on special cases. So Yarming and I proved something in 2009. and Owen Hillion in 2012 proved something. He considered the case of a particular fixed random variable, and you convolve it with a binomial, so you kind of shift it according to a binomial. So basically what happened was that Erwan got in touch with me. He emailed me and said, oh, hi, you don't know me, I'm Erwan. I need to solve this problem for my thesis. And I said, yeah, this is a special case of this Shep-Olkin conjecture. It's not been known, I don't know how to do it. But why don't we write a grant and get some money and you come to Bristol and we work on it together? And this is actually what happened. So we got some money, we were lucky, Erwan was able to come, we were able to think about this for a couple of years and maybe make some progress with it. So really where we started with this binomial case. We wanted to understand why the binomial case makes sense. And so what we wanted to do was we wanted to embed it in this sort of bigger world of optimal transport. So what we wanted to think was, if you've got a binomial NP and you're going to transform it to a binomial NQ, then it's kind of clear how you want to do that. You want to do that by going through the family of binomial n whatever. So you want to always stay, when you're going from one binomial to another, you want to stay within the binomial class as you do it. So the problem with this is that most of the standard definitions of discrete geodesics don't do this. If you look at what the definitions of standard discrete geodesics are, they don't follow that path. If you say, how do you interpolate from this to this, they do something else. So we had a kind of aesthetic judgment, was that this was the route we wanted to go. So we started off by basically working backwards and saying, this is what we want the geodesic to be. Given that we want this to be the geodesic, how do we fiddle the definition of what a geodesic is to make it that this is a geodesic? This was our kind of philosophy with this. And I don't have a lot of time to get into a lot of detail on this, but just to kind of talk about how the binomial case works. If I write delta star for the finite difference, so this is the finite difference in the other direction, this is the kind of left finite difference. What I can do is I can define this PT to interpolate exactly in this case. So I'm interpolating the binomial parameter between P and Q in a linear way, and I can just write down the binomial mass function. I can say, okay, here is the binomial mass function, and what I want to know is, I want to know the derivative of this, right? And this is a pretty simple calculation. I know what everything is here. This is all in closed form. And what I can do is I can see that the derivative of this mass function is it's delta star times something not too bad. So it's nq minus p, so it's a constant times. And then this is the thing that's really annoying. It's no longer in terms of binomial n anything. It's in terms of a binomial n minus 1 something. And this is the thing that's really annoying, is that you step out of this binomial n world into this binomial n minus 1 world when you take a derivative. So luckily, I'd seen something of Yarming's around the same time, which was actually, you can always step back up. That if you have, this isn't an obvious fact, but if you play with the distribution functions, you'll convince yourself, a binomial n minus 1p is a linear combination of a binomial np and a binomial np. It's a linear combination of the things that you're interested in, and there are these weights. There's k plus 1 over n and 1 minus k over n. So what we'd like to do is we'd like to rewrite this. Instead of thinking about this as a binomial n minus 1, we'd like to rewrite it as a linear combination with weights, well, this is kind of alpha k plus 1, and this is 1 minus alpha k. So this was our idea, that we try and express things in terms of the derivative being a kind of weighted linear combination. And so this is what we did. We said, okay, well, we might want to do this in more generality, but for now, what we can say is that we'll write dft by dt is delta star of a constant times something that is a linear combination of these mass functions. So this is a linear combination of the k plus 1 mass function and the k mass function. And so because of the way I've picked this weight, because of the fact that this is the weight 1 higher than the weight I'm taking off there, it turns out that this GT star actually is, GT alpha is indeed a legitimate mass function in the way that it should be. So in the binomial case, for example, it turns out that alpha t of k is k over n. It's very simple. But what we did was we took this as the starting point, and we we deduced a discrete version of the Benamou-Brenier formula. So the Benamou-Brenier formula tells you about geodesics. It kind of thinks about geodesics in terms of fluid flows. And so what we were able to do was sort of, from this motivation, we were able to come up with a characterization of geodesics that says geodesics are nice in that they satisfy the kind of variational characterization. I'm looking at the time here. I think I'm going to skip this and I'm just going to show you this formula and say it's not very nice, is it? But this is the kind of point, is that what you can do is you can write down a variational characterization of the distance between f0 and f1 as it's the smallest value along all the paths and all the possible weightings of the sum from 0 to 1 of a kind of weighted square to do with the g's and the v's. So we were able to write something down that was a variational characterization, and just, you know, we kind of post hoc fiddled it. We said that anything that satisfied this condition we're going to call a geodesic. So anything that satisfies this condition we will say is a geodesic, because we know that this is a geodesic, and so we've retconned it, if you know that word. We've retconned it that this path that we want to be a geodesic is a geodesic. I started a little bit late, so I'm going to finish a little bit late. I'm sorry about that. But I want to show you the theorem, just because we were happy with the theorem. So what we tried to do then was to understand, along these kind of paths, you know, we've got this definition of a geodesic. In this sort of, you know, Sturm-Lott-Villani kind of world, we know that going along their geodesics, the entropy is a concave function. And so this is why we think Shepolkin might be true, that, you know, we go along one of these geodesics, it's a geodesic in this sense, therefore the entropy is going to be concave. So what we came up with was, we came up with a kind of three conditions, so three conditions that kind of come out of these calculations quite naturally. So the first condition, well, they're conditions on the alphas to some extent. So the first condition is that the alphas should be increasing in k, so we call this k monotonicity. Secondly, the alphas should be increasing in t, so we call that t monotonicity. And so those two directly are satisfied, right? If you go back and you look at alpha t of k being k over n, you can see that it's an increasing function in k. It's monotone in t. I mean, it's not a very interesting monotone function in t, but it's a monotone function in t. And then the third condition is a sort of another of these generalized log concavity conditions. So the third condition is generalized log concavity, that we say that, again, sort of the weight of k plus 1 squared is bigger than the weight of k plus 2. And this is what we called generalized log concavity. And so putting these three together, putting these three together, we were able to prove the following theorem. The following theorem says that if these three conditions hold, if k monotonicity, t monotonicity, and GLC hold, then the entropy is a concave function. Right, so you think you're getting coffee now, because you think I'm going to say, and these conditions are satisfied for the Shepolkin yada yada, and we're done. And it turns out they're not, and it really made us cross. So what it turns out is that the t monotonicity condition doesn't always hold for Shepolkin paths. Not all I mean, there's a big class of them for which it does hold, but for general Shepolkin paths, particularly Shepolkin paths where some of the probabilities going, some of the parameters go in that direction, some of the parameters are going in that direction, the t monotonicity doesn't hold. And so what we had to do was we had to introduce something that I'm really not going to get into, that we call condition 4. So condition 4 is what we had to do because t monotonicity didn't work in general. And of course, condition 4 is designed such that it does hold for Shepolkin paths, and so we were able to prove, as a result, this Shepolkin theorem, that for any n, the function from p to h of p is concave. But if you try and track it down in papers, it turns out that it is actually across two papers. That the first paper was in the Annals of Probability in 2016, and this is the case where all the pi primes have the same sign. So all the pi primes have the same sign. Essentially, this t monotonicity condition holds, and so we were able to prove it. But what it turns out is that in some sense this is the hardest case. I mean, we thought we'd only scratched the surface, but actually this is the hardest case, and so we were able to kind of join the dots and sort of tie it together in a paper a year later in Bernoulli. So, you know, in retrospect, you know, it should have all been one paper in one place, but of course it never quite works out like that. Okay, so I am going to finish. I'm going to leave you with an open problem, just because I can. So the open problem is this, that the same thing should be true for Renyi entropies, right? I mean, we believe that Renyi entropies are similar to Shannon. Well, we know that Shannon entropy is a Renyi entropy, and so if something's true for Shannon, then it should be true for some Renyi at least. So my conjecture is this, I'll skip back at one, that there is a critical QR star such that the Q Renyi entropy is concave for Q less than QR star, and that it's not always for Q bigger than QR star. Corresponding conjecture for Salis, because Salis and Renyi, although they're functions of each other, just because one is concave doesn't mean that the other is. You know, the concavity, you get into second derivatives and the chain rule and stuff. So there is a corresponding conjecture for Salis entropies. And there's a sort of meta conjecture of this, which is that I conjecture that the Renyi, it's true for 2, and for Salis it's true for something not very nice. And so maybe that is a suggestion that Renyi is more natural than Salis in this context. The reason where these values come from is I have, for values bigger than this, I have examples where the entropy isn't concave, but I can't find examples below this. So this is why the conjecture is anchored where it is. But this is my belief about these numbers. So it would be an interesting thing to go back to, and you know, maybe we need some more ideas. I can't quite make it work yet, but to understand in a sort of bigger framework why these Q entropies are concave in general. Okay, sorry for gabbling, but thank you for listening.
Thank you. So I think we can afford some questions.
Hi.
So for the result for monotonicity for the entropy, so for the continuous random variable, they have a result, settling the 50-year-old conjecture, and you also have a result which looks very much similar. So other than the similar looks, do they have any more deep connection? For instance, the proof or
no, not particularly. So their proof is via so the Artstein-Bull-Barton-Orr is via this kind of variational characterization of Fisher information and optimal transport and things like that. Ours was built out of kind of sealing wax and string. I mean, it was literally number crunching to make it work. I suspect there may be a more insightful proof of our result in terms of sort of optimal transport or something that we didn't find at the time. Their result is interesting because it gives you an EPI. Our result doesn't really give you an EPI. I mean, it gives you a few things that you can argue look a bit like an EPI, but we set off to do this because we wanted to prove a discrete EPI, and we didn't get a discrete EPI out of it. And that's, as you know, a whole open area to know what a discrete EPI would look like.
I have one more question. So
Okay.
you have this nice theorem with these conditions, monotonicity, T, K.
Yep.
Is there at least one example which satisfies your theorem? I mean,
yeah. So as I say, so Shep-Olkin paths where things are going in the same direction. So sort of trivially, the binomial satisfies this condition. So So these three. I mean, I said that the binomial, these first two conditions are satisfied. The third condition is actually, as I say, this is literally what's called Newton's inequality. I'm kind of standing on the stage next to the guy's apple tree. This is the Newton inequality holds for binomial, but it holds more generally. So I think I'd like to say this is true for all Bernoulli, for all Shep-Olkin paths where the PIs are all increasing, where everything's going in the same direction. So kind of where there's a sort of stochastic domination from one to another. Right.
In the slide in which you showed the relationship between thinning and scaling, you mentioned that for the relative entropy it would hold for any random variable, but for the entropy it would hold for only ULC. Is that easy to see why? Because after all, one is derived from
no, it's not obvious. No, it's not obvious, and it's sort of slightly surprising, I think. So yes, so the same. So this result is that result there is true if X or ULC. The same thing if you just write, instead of H you write D, and you write it for D is the distance to the nearest Poisson. Then that is true. Obviously the sign flips, but that's true without any assumption on ULC. And again, it's an example of where the discrete case is messier than the continuous case. In the continuous case, entropy and relative entropy are basically equivalent, right? I mean, you know, the relative entropy to a normal is just a constant minus the entropy. So if it's true for one, it's true for the other. Whereas in this case, you end up, you know, the relative entropy involves these not very nice expectation of log of x factorial terms. And so somehow I think this is saying that the relative entropy is more fundamental, maybe, that the relative entropy is more fundamental than the entropy, that it's true for the relative entropy. And I mean, Yarming's proof is very simple. I mean, it's basically data processing. There's an argument with pretty much with data processing that says that this is true.
Okay, so thank you so much.